Hey, hi guys, welcome back to my YouTube channel. It's a day 3 of 100 day geospatial data analysis series. In this video, we will understand what actually the electromagnetic radiation is, and we will deep dive into its property. Without delay, let's get started. In remote sensing, when the light energy is generated from the surface, either it is from sun or the artificial target, it travels towards the surface of the earth as well as reflected back to the sensor in the form of electromagnetic radiation. Just like it's a sun. Okay, the light is generated from the sun at this time. Let's talk about the passive remote sensing. And there is a surface. This is a ground surface, and these are the objects present on the surface, and then the light is reflected back to the sensors, and it's a satellite here, and then it sends the information to the analytical station, and it is used in the application. Okay, when the light is travel from the source to the target and then reflected back to the target, it travels as a form of electromagnetic radiation, right? And what actually the electromagnetic radiation is, and its electromagnetic radiation can be defined as a form of energy. It's a form of energy, and that is generated when the electrically charged particle moves through the matters or the vacuum. This light is electrically charged particles. When it travels into the vacuum or the matters, the electromagnetic radiation is generated, right? Alternatively, we can say that it can be also produced by oscillating the magnetic and the electric disturbance. Okay, let's say this is the direction of propagation. We can, okay, let's write like this, something like this. And okay, let me write, yes. And this is how the electric field is generated. And this is how the electric field is generated. It is generated in the vertical axis or the vertical plane. Similarly, and it is perpendicular to that of the direction of the propagation. It is the direction of propagation of the wave. Okay, and let's take another, and this is another wave is generated, which is propagating in the horizontal plane. And so this is, as a whole total, this is called the electromagnetic radiation, right? Okay, let's move to the another slide. And the first requirement of the remote sensing is to have the energy, right? Any of the remote sensing need energy source, either it is passive or the active. The one difference is in the passive remote sensing, the energy is generated from the sun. In the active remote sensing, the energy is generated from the artificial source. And at the both case, we need a energy source to eliminate the target, right? This is the surface, there is an object, and in both of the case we need at least one source that can eliminate the target unless the signal is emitted by unless the energy that is being emitted by the surface. At this, when the energy is emitted by the surface, at this time we need not the energy source, and this energy is in the form of the electromagnetic radiation. This energy is in the form of electromagnetic radiation, and it consists of the electric field. This is electric field, which varies in magnitude in direction perpendicular to the direction in which the radiation is traveling. This is the direction where the radiation is traveling, and this is oscillating in the magnitude, oscillating in the direction perpendicular to the direction of the propagation. And a magnetic field oriented at a right angle to the electric field, and there is also a one field that is called the magnetic field, which is also perpendicular to the direction of the electric field, and also the perpendicular to the direction of the propagation. So all these directions of the propagation, electric field and the magnetic field, are mutually perpendicular to each other. Both of these fields travel at the speed of, and both of the electric field and the magnetic field travel at the speed of the light, which is 10 to 3 into 10 to the power 8 meter per second. And what is the property of the electromagnetic radiation? All electromagnetic radiation has the fundamental properties and behave in predictable way according to the basic of wave theory, right? The properties of the electromagnetic radiation can be defined by the wave theory. This theory describes the electromagnetic energy as traveling in the harmonic fashion, something like they have same magnitude all around the all of the time, and they have the same constant phase difference or the constant wavelength, and that so it is called the harmonic fashion at the velocity of the light, and they travel with the speed of the light. And two characteristics of the electromagnetic radiation are particularly important for understanding the remote sensing. We need to understand what actually the wavelength and what actually the frequency. To understand, if you understand what actually the wavelength, what actually the frequency, then we understand the what actually the electromagnetic radiations, and which electromagnetic radiation is useful for our remote sensing purpose. Okay. And what actually the wavelength? It's just a distance between two successive crests or the two successive rod. Okay, it is the length of the one complete cycle. It's the length of one complete. Okay, let me draw the straight line here. If I start from the this, okay, if I start from here and if I into here, okay, let me draw this in this region. Okay, this is, yeah, and I can redraw it is if I combine this portion and this portion, okay, we can draw the this is the, and it is the distance, it is the length of one complete cycle. This is called the wavelength. And what is called the frequency? Frequency means if I take the radiation something like that, and if I take this point, if the radiation is travel into the certain direction, and if we take this point, and the frequency can be measured as number of the complete cycles that is passes through the point per unit time per second. Okay, and it is measured in the unit of hertz Hz. And okay, and what actually the wave model define is, the wave model provides the relationship between the wavelength and the frequency and can be expressed mathematically as c is equal to lambda v. Okay, the c is the speed of the electromagnetic radiation, and lambda is the wavelength of that radiation, and v is the frequency. So frequency and the wavelength are inversely proportional to each other. Okay, let me go, and c is equal to lambda v. C is the constant, right? We can write lambda is equal to c upon v. C is constant, so we can write lambda is inversely proportional 1 upon v. So they are inversely proportional to each other. If the lambda, if the wavelength of the radiation is larger, then its frequency is low, and vice versa. So, and what is called the particle model? Although many characteristics of the electromagnetic radiation are easily described by the wave theory, that is c is equal to lambda v, and another theory known as the particle theory offers insight into how the electromagnetic energy interact with the matters. Okay, the electromagnetic energy is generated from the source and travel through the atmosphere, interact with the surface, right? And to describe how the electromagnetic radiation is interact with the surface, we need to understand its particle model. And this theory suggests that electromagnetic radiation is composed of the very small packet of the energy, and it describes the electromagnetic radiation is made from the very small packet of the energy, right? Called the photons or the quanta. This packet of the energy is called the photons or the quanta, and this is proposed by the Albert Einstein. The reason that photons are able to travel at the light speed is due to the fact that they have no masses, and we already mentioned that the speed of the electromagnetic radiation is equal to the light, and then Albert Einstein proposed that if any of the particle if travel with the speed of the light, it doesn't have any masses. So if it has some masses, then if it travel with the speed of the light, its mass will go into the infinity. So quanta have no any of the mass. So Einstein famous theory is equal to mc square cannot be used, and So at least the quanta have some small masses. If we apply these masses here, then the energy is moved to the infinity, so E is equal to mc square cannot be applied here. So Planck's devise a new formula which describes the relationship between photon energy and the frequency, which can be mathematically described here. So here is the rule of the Planck's, comes the rule of Planck's. So Q is equal to hv, right? And he Q is the energy of the, he gives the formula of deriving the energy based on its frequency. And so here we see that Q is called the energy of the quantum, H is called the Planck's constant, 6.626 into 10 to the power minus 34 joule second. And this is the smallest unit that is ever drive in this universe. And if we already discussed, B is equal to the frequency. So so here we see that Q is equal to hv, and from the wave equation we already know the C is equal to hv, so it's equal to lambda v. C is equal to lambda v. So we can see that V is equal to C upon lambda. If we write in the form of frequency, then we can write Q is equal to hv, or if you want to write into the relation with the lambda, then we can say that as C upon lambda. And thus we can see that the energy of the quantum is inversely proportional to its wavelength. The longer the wavelength involved, the lower the energy constant. So if we next video we are discussing about the electromagnetic spectrum, where it is expand from the gamma ray to the radio wave. Gamma ray have the highest frequency, and the radio have the lowest frequency. So energy of the gamma ray is highest and the energy of the radio wave is lowest. That's all for today. See you in the next video. Thank you.